Alright, good afternoon. Here's part 2 out of 2 for review for the unit forces. Okay, so before we just went over force of gravity, force of friction, two-dimensional forces, and Hooke's law. So now we're going to go into tension. So we kind of learned out what tension was. Tension is just another word for force, but it's the force of kind of a long and skinny object like a rope. Okay. So generally we always do ropes as our tension questions. Okay. So here we have a box that you're pulling along the ground. These types of questions could be different. Sometimes they're ones where there's boxes hanging from a rope. So they kind of represent when you're pulling on something, the force that's opposing your pull. Okay. So here, if you're pulling on this rope here, its tension is going to be directly related to the arrow that's going in the opposite direction. So let's draw a free body diagram on all the forces that are acting on this box. We have force normal, or it's the force that's pushing up on the box, or the ground pushing up on the box. You also have your force of gravity downward. Here we have force of friction going that way, and then we have of course our F push of that rope on the box. Okay, so that tension is actually going to be the same as that force of friction, just the opposite arrow there. Okay, so our goal is to find this force of friction, and that's what our tension is going to be. So our tension is going to be force of friction. So our force of friction, we know we always have to use that equation there, mu Fn. Is the ground flat? It is. So we know that Fn is going to be the same as Fg, only when the ground is flat. So our T is mu Fg now. Okay. Our force of gravity is just mass times acceleration, so we can go mu m times g. Sometimes g is written instead of a for acceleration if that's 9.81. So it's going to be T is mu. They don't give that in the question, so let's write one down. 0.25. Let's say they give that in the question. So it's going to be 0.25. Our mass is 5 kilograms, and our gravity acceleration is 9.81. So overall, our force of friction is 0.25 times 5 times 9.81. So let's type that into the calculator. And I got 12.3 newtons because it was a force of friction, 12.3 newtons. So that's how much force you need to push to start the box moving. Okay, but you pull the box so it starts moving, so that means you need a force of at least 12.3 newtons. Okay. The funny thing is, if you actually pushed more than 12.3 newtons, the tension would not increase. Okay, the box would just move faster. Okay, so 12.3 newtons would be the tension, and it would actually be the maximum tension of that rope. You wouldn't be able to go any higher than that unless you increase the mass of the box. Alright, so now let's go to this next question. Tension, you pull a box so that the box just starts moving. Okay, just like the last question. Let's put a mu of 0.25 again so that we can compare between the two. What is the tension of the following rope? This was more so if there was two-dimensional tension, but I'm going to go over it anyways. So here you have 30 degrees, which is right in here, 30 degrees from the horizontal. And this time you're pulling kind of upward, not just sideways. Okay, but it's the same question. So let's just find the components of this. All angled questions are the same, kind of. You just need to find the x and y, the components. So we have the x component of this, and we have the y component of that. Okay, we just know that that's 30 degrees. Okay, so our tension of this rope is going to be T. Okay, this one down here is going to be T cosine or sine. Let's see, it's right beside the angle, and cosine uses adjacent, so we're going to use cosine 30, and we know that this y component is going to be just your tension times sine 30. We use sine because it's opposite the angle. So we have those two values there. Let's draw a free body diagram. We have the normal force, the gravity force, the push force, and the friction force. Okay? So overall it's hard because your tension here is not going to be directly the same as this one. Not like the last question, because they're not directly opposite. Okay, what's directly opposite this force of friction though? It's this one here, the x component, T cos 30. Okay, so we can write T cos 30 is equal to force of friction. Okay, so let's do the same thing as before. Our force of friction, it actually doesn't change from the last question, 5 kilograms, and it's still the same 0.25, so we know our force of friction is still going to be 12.3 newtons. Okay, so I'm just going to skip a whole bunch of steps because we just did it. 12.3 newtons for that, and it's going to be T cos 30. Okay, so now I have this equation. I got to solve for the only unknown, which is our tension. So what do we have to do? We have to get T by itself. That means T is being multiplied by cos 30, so let's do the opposite. Let's divide by cos 30. So it's going to be T equals 12.3 divided by cos 30. So it's 12.3 divided by cos 30, and we should get a tension of 14.2 newtons. Okay, so if you start pushing in a more upward fashion, not directly perpendicular to the ground almost, or parallel to the ground, you're going to have to push with more force. More 12.3 versus 14.2. So you're going to have to put more force in there. Okay. Alright, so that one's done. Let's go to the last section. We have Newton's laws. We went over this last week, and it's Newton's laws. We have 1, 2, and 3. Number 1 is inertia. A body will continue to move at the same speed and in the same direction for as long as there are no unbalanced forces working on it. Okay, unbalanced forces, again, are forces that cause acceleration or deceleration. Okay, so overall is heavier objects like the direction they're going. So example, a big truck that's going in a certain speed, the faster it goes and the heavier it is, the more it will want to continue and the harder it is to stop it. Okay, so inertia is something just wants to continue still or wants to continue moving. We have the second law. If unbalanced forces acts on a body, the body will accelerate. And it's saying the sum of the forces in the net direction, or the forces in the net, is going to be equal to the sum of the forces. Things accelerate or decelerate when a force is applied. So an example here is if you have a box, okay, and you push on it here, if there's no thing pushing that same way over there, say there's nothing also pushing on that side, that's called an unbalanced force because there's nothing on the other side that is equal and pushing backwards. Okay, so an unbalanced force is like that. For example, if you pushed a box on a ground and say you only pushed with 1 Newton and it didn't move the box, okay, because maybe the force of friction max was 3 newtons. Say you had to get at least 3 newtons to start it moving. Okay, so if you pushed with 1 newton, the force of friction would push back with 1 newton. So that would be a balanced force. Therefore, it wouldn't move. Okay. Another example is force normal and force of gravity are an example of a balanced force because it's not moving up or down, so it has to be a balanced force that's acting on it. That has to be the same as that. Okay, so those are examples here. And here, action and reaction is our third one. If two bodies act on one another, the force the first body exerts on the second will equal the force the second body exerts on the first body. Okay, an example is you push on a wall, it kind of pushes back on you. Okay, it makes a balanced force back on you. Okay, so everything that touches, that exerts one on the other, I tap this pencil on the desk. Right when it hits, it puts a force on the desk, but the desk also puts that force back on the pencil. Okay, so how do these three laws work when someone shoots an arrow with a bow? Okay, so we have a bow here and an arrow. So you're going to shoot it. It's going to go. Let's say there's a nice bullseye over here. Okay, so here is you pull back the arrow and you release. A force works on this arrow to get it moving, an unbalanced force. Okay, and that's the force of kind of the elastic string here that you pulled on, and that works on here, and it causes this arrow to move very fast. You could say the first law makes it move, and the arrow will continue forever in that direction unless any unbalanced forces work on it. We know that eventually it will stop or slow down, so what works on it is air friction, is an unbalanced force that slowly works against it. Okay, so that's an unbalanced force that causes deceleration. Another thing is the acceleration of this caused it to accelerate to begin with, and then once the force was done with, eventually it started to decelerate because of the air friction. And last of all, action-reaction. It's going to hit this board, and it's going to cause a large force to be applied to the board, but then the board is going to apply that force back on the arrow. Okay, and it'll essentially stop the arrow. Okay. Anything else to add there? I think that is it for that type of example. Here, a model rocket has a mass of 0.38 kilograms. It accelerates vertically to 52 meters per second in 1.5 seconds. Okay. This is what is the average acceleration first. So let's find that. This is a bit of kinematics. Oops. We can have our velocity over time is acceleration. Okay, so it went to 52 meters per second, and then usually you minus your starting time, so final minus initial velocity, and then your time is 1.5 seconds to 0. Okay, so overall it's 52 divided by 1.5. So what we're saying here is it was roughly 34.6 meters per second squared of acceleration averagely for this model rocket. So again, it's a model rocket that wants to go up. Okay, so this is dealing with Newton's second law, where you have net forces. Net just means when you take one and you subtract another, it's the overall force that's acting on it once you subtract the two. So what is the unbalanced force on the rocket? Okay, so it accelerates upwards, so there has to be an acceleration on that rocket, an unbalanced force on that rocket. So here it accelerates vertically. So what is the unbalanced force on the rocket? It's the thrust, I would say. And when it starts going, it's eventually going to be also air friction working against it, because it's not going to go up forever, right? Eventually air friction is going to slow it enough to stop it. Given gravity as well, what is the overall thrust of the engine? So let's calculate some values. We know here it's force in the net direction is mass times acceleration. Its overall acceleration is 34.6 net, because that's what's actually happening, and its mass is 0.38 kilograms. 34.6 and we get 13.15 newtons is going to be how much overall or net force that's working on this rocket. Okay, so that's the net force, which means it's one minus another force. Okay, so what's that 13.15 going to be equal to? it's going to be equal to its overall thrust, the amount of force upward, minus the overall force downward. Okay, so you have an air friction working down against it, and you have a thrust working up on it. Okay. I guess one thing to add is gravity also works on it. Here it's saying, given gravity as well, what's the overall thrust? So they're saying the air friction does not exist, which is not true, but for our purposes we can say that. Okay, so they're saying if you take the thrust and you minus the force of gravity, what's your net? Okay, we already know what the net is. It's going to be 13.15. We just have to find out what the overall thrust is going to be then, okay, before you minus that Fg. So our F thrust minus our Fg, which is mass times acceleration, 0.38 times 9.81. And you end up adding this to that side, and you'll get your F thrust. Okay, thanks.